Okay, for people who are joining us here, the objective is to try and make a computational essay that explains a little bit about epidemiology as relevant to the coronavirus, COVID, etc. So we have, I'm a total amateur in this area. Fortunately, we have uh, Bob here who actually knows about this kind of thing, and we have several other people who also know about aspects of this. So I think what I'd like to start on is the most basic thing, which is, the most basic thing one hears is there's an epidemic, it's going to be exponential increase in the number of people who are sick. And I'm just curious if we just take that as the 0th level model. So maybe we can start actually filling in our actual document here. And this is clearly showing okay. So, and I'm not sure if it's going to work to really write everything out here, but let's see what we can do. So I guess my first question would be, Bob, I mean, if we were going to just say it's exponential increase, the total number of people who have been infected, that's the most naive thing. But when you start filling in models, you're going to have some delay time to infection and things like that.
Right. So this is basically the simplest model right here. And the very first step from the susceptible to becoming infected is the part that shows the exponential growth.
Right, but okay. So just the very naive thing. Let's imagine that it takes that each person is going to infect, let's say, 5 others.
Okay.
And it's going to take a week for that to happen.
Okay. So then we would write a differential equation for that.
We don't need to write a differential equation. It's just an exponential.
Okay, well, integrating the differential equation gives you the exponential, and so to write the exponential straight off.
Okay, so let's assume, okay, as a 0th approximation, just assume that each person infects 5 others, and it takes a week. Okay.
Okay.
So that means that so after T weeks, the number of infected people will be, and it's basically just 5 to the power 5 to the power T, right?
No, I don't think so.
Why not?
We would start out with, well, initially nobody's infected. And
but assume you start off with 1 person. So at time 0,
right, one person is infected to start, and
see, the thing that's unrealistic about this, and what you are reacting to, is you're assuming that there are new people at every stage to give this to. And that's where we're about to start running into something non-trivial, because in reality, let's assume that the actual sort of social network of the world is something like, I don't know, let's make a random graph here, is something like this, right? This is no longer going to be correct, because spreading from this point, you don't get to spread to exponentially many more people. Right, so I'm just curious.
Well, actually, on that particular network, because it's a small world network, it'll be pretty close. If you picked a different type of network, then then it would be less exponential.
Let's find out. We can say, so here's our network, and we can say this is our graph, and so now we can say, what do we want to do? We want to say neighborhood graph. We want to know how many nodes there are in a neighborhood graph, starting at that, going out. Okay, so that's what we get. That's the number of people. Actually, if we did something like this, we said highlight graph of that original graph, and we go out there. Okay, so that's where our contagion is starting up. If we go out, let's go out 4 steps here. Okay, so now we've infected that chunk of the graph. So I think what we need to know is how many vertices are there in this as a function of t. Is that right?
Right, right.
So you're going to
although you might want to make the underlying graph a bit bigger, because as it becomes, if you go out 4 steps and you're already hitting most of the graph, then it's going to start hitting the edges of the graph quickly.
All right, but let's see that actually. Okay, so if we go out to 10 things here, okay, so yeah, so it limited out because we only had 300 nodes. This limited out very quickly. So that okay, so it increased and eventually it hit the edge because everybody got infected.
And I bet if you say ratios of that it'll be pretty exponential.
Okay, so let's look at ratios of 102.
At least at the beginning.
Yeah, it is fairly exponential.
And actually, something that's also nice is that I believe that the Watt-Strogatz graph distribution function. So by default, its third parameter is 2, which means that basically the average number of neighbors is like 4 or something like that. So if you change that, I bet it'll change the exponent as well.
Oh, well, let's try that. Okay, so let's try making a bigger version of this graph. So let's say, I don't know how big we think we can deal with. Let's do 10,000. Okay. Okay, so there's our graph, and it's not showing it explicitly here, but let's now do this.
In fact, what's the population of Champagne? We could use that as a number.
I think it's on the order of 100,000.
Okay, well.
Although right now it's probably a lot less, because I know they're like something like 50,000 students and 40,000 faculty at UMI,
they've all gone home. Yes.
Yeah.
Right. Okay. So anyway, so let's try this, and let's look at oops, we only did 10 steps. We can probably go out to like 30 steps here.
The small world networks, not really, but yeah.
Yeah, right. So it hits everybody after a little while. And Sandra on the live stream is suggesting list log plot. Yeah, it's pretty close to linear, and then hits the edge. Okay, so
it's interesting, by the way, that it doesn't. You might imagine that sort of as it reaches the ceiling that it would slow down, but it pretty much doesn't.
Right. Okay, so I'm curious. My first question here. So this is exponential increase, just like my super naive model is here, right? Except in this case, you say, well, Christopher says it's that there's a parameter in here. Let's look up what the parameter is.
Yeah, it's the third argument. It's the third argument, which is a little bit cryptic, but it basically directly corresponds with what the average degree is going to be.
Okay.
So you can also use, by the way, another for what you're doing right now. Arguably, you should be using this other one, the Barbarossi something or other. Yeah, because that one has a more realistic degree distribution, and so it won't be as perfectly exponential. Probably.
All right. Well, let's try that. But let's first of all, let's just get some basic information here. So I mean, on this exponential basis, this would predict that it would take how many weeks? I don't know. What's log to the base 5 of like going to, oh boy, I need to turn that into oops.
You can just say n of that, I think, and it will work actually.
Okay.
But it'll be in log people or something. Okay, never mind.
I think we need to say that we need to depeople. We need to just say quantity, magnitude. Okay, n of that. Since I don't think we really need the precise. Okay, so that would say it would take 14 weeks. And so first question is, so in this network, it's saying basically the same thing. But your claim is that in this other network, which has a where in this network, if we look at the degree distribution, so you're saying in the case of this GR network, we're saying that if we say vertex degree of GR, and let's make we make a histogram of that. Okay, so that network is sharply peaked around 4. So you're saying if I use this Barabasi Albert distribution, what are its parameters? And then the K, what's the K?
I think a reasonable K is like 5.
Okay. Okay, so this is a network where I guess it's grown by successively attaching new nodes to the network, right? So you're saying if this is, let's call this BGR, you're saying in this network, if I do the same degree distribution, it will be a broader distribution.
Well, actually, you'll see it'll be a bit broader, but it'll be also skewed in a very different way.
Wow.
But you see, it goes all the way up to 25.
Yeah, it's probably log normal distributed, would be my guess.
Okay, so let's look at our growth story with this. So in the case of the Watt-Strogatz distribution, we had basically exponential growth until we hit the limit. So let's take a look at this one here. Let's see what this does. So you're saying, so what I should do here is I should do my 10,000 there. That will be my graph, 50,000 edges.
So to be fair, between the two models, arguably you should say, as a third argument of Watt-Strogatz, you should say comma 5, because I believe that'll make it so that they have approximately the same average degree.
Okay.
You can check that. But
well, let's make this one 4 just for the hell of it. Okay, so now let's say this. Wow.
That pegged it immediately.
That's bad. Okay. And that's because presumably, so that's interesting that makes such a big difference to how fast you can spread on the network.
So this is one of the things I was actually looking at recently, which is the extent to which it matters. In one model, what matters is the mean degree, but another model, it might matter what the max degree is. And so I think in this case, what's mattering is probably something like the max degree or something close to the max degree.
Right. Well, so in other words, you're saying that there are folks who spread. I mean, if we look at this version of the graph, we could explicitly look at spreading down here. So if we look at this and we just say highlight graph of that neighborhood graph, ag 1,3. Well, by 3 we know it's going to be the whole graph. So at 1, wow. So that person already had spread it to all those neighbors. Even though, but in this case, the minimum degree is already 4. Well, the other one, the average degree was 4.
Yeah, so I think you should try and adjust the parameters so that they have the same average degree, because otherwise it's kind of unfair to compare them.
Okay, but so what is the average degree here? So I've got to get the mean degree. You think it's the mean degree or something else that I should?
Let's say the mean degree for fun. I mean.
Okay, all right. So then let's take this, and we could say for this thing here, let's actually work that out. So
if you want, you could. Yeah, go ahead.
Well, so let's say vertex degree. Let's only do 1,000 here. Let's just do 500 here, and let's say vertex degree of that, and then let's get the mean vertex degree, and might as well just numerical vertex degree, doesn't matter. Okay, so that's going to be 7.96. Okay, so now we want to vary this parameter. What should we call this? We could call this K or whatever. What we want to do is let's first of all just plot that as a function of K, between 2 and 5 or something. What happened here? Oh, does that have to be an integer? No. 5, 2.06. What did I do wrong here? Oh, silly me. I'm asking to plot. I see. That has to be an integer. Is that right? That parameter has to be an integer, apparently.
Yes, I think that has to be an integer. Each new vertex has that many edges, yeah, so it has to be an integer.
Okay, so what we're seeing there is that with k of 2, we would get a mean degree of about 4. So that suggests that we try one of these with a k of 2. Let's get a random graph here. Okay, so let's do the same thing just for this. Just to see what it looks like. Okay, it still seems to spread quite rapidly here, but let's try doing our back to this whole story here of getting that. Okay, so let's do this. Let's redo that, but now with changing 4 to 2. Didn't make much difference. Still goes up very rapidly.
Well, so one thing is that this other graph distribution has less realistic clustering. So maybe it's that, if you have more clustering, it slows it down. But
so, I mean, okay, so first thing we're realizing here is both of these show essentially exponential growth. They both, even though, so I'm curious in Bob's differential equation model here, for example, how does that capture the kinds of things that we're seeing in these networks, or is that sort of a different type of modeling?
It's captured in that term beta times lambda of t. Lambda of t is the force of infection, which is basically the number of infected people. And the product of S and I, the number of infected people, is the rate at which you get more infected people.
Right. But that's assuming, but that's not capturing what happens in the network, right? Because in a network, that's assuming it's like, this is like you would do in chemistry, where it's a certain number of molecules just bouncing around, and there's a certain density of molecules, and that determines how many reactions they're going to be, which is not the same thing as what you have in a network. I mean, if the network is in some sense static, you're going to get completely different phenomena than if you have something which is basically a bunch of molecules that, where the molecule you're going to react with is somebody you've never seen before, right? I mean, in other words, you are essentially assuming, as Boltzmann did for the H theorem, kind of a molecular chaos assumption. You're assuming that these molecules, or in this case, people, are, you're making exactly the assumption that's made.
It's a homogeneous, well-stirred mixture. Yes,
right.
It's that assumption, and what you're modeling is not, but probably more realistic on the smaller and more discrete scale.
Right. But so what matters? I mean, in other words, does the social network structure matter, or is it? I mean, maybe we should first of all go through the differential equation story. So I mean, the most naive differential equation story is a fixed beta lambda of t, which is basically just going to give you a pure exponential. Is that correct?
Yes. If lambda really is constant, then it will give you an exponential.
And why would lambda vary?
Because each time you convert an S to an I gets bigger, and lambda is a function of I.
But it says it's a function of t here.
Well, a function of yes, but if you look at the last equation there in the next set, that's what lambda is. It's the number of infected people, the force of infection. So it's a nonlinear differential equation.
Well, so hold on a second. So you're saying, I mean, so this really is just, it's like a chemical rate equation type thing.
Exactly. Yep.
Okay.
And it's assuming that if you do this on a large enough population, like for a whole country, that you can get away with it.
I don't think that's the. I mean, that seems wrong to me. I mean,
well, partly, I mean, the epidemiologists adopted this back when they couldn't do what you're doing on the left.
yeah, I understand.
So,
but so okay. So, I mean, it is interesting that this is okay. So, with what I would call the people chaos assumption, that is that people are are well mixed and stirred and so on. Then, well, let's understand what this implies, and then let's compare it with what you would get if you have more structure to the population, so to speak. So okay, so what you're saying here is people get sick at a rate that's proportional to the number of infected people.
right. Yep. The more sick people around, the more likely you're going to get sick.
Right. You're right. I mean, okay, so fine. So now what's happening in this case?
This case here, we're adding births and deaths to the model.
But
in other words, if you're running the model long enough, then
yeah, okay, fine.
You have to take that into account.
Right. Birth is not something that's we're dealing with here.
No.
Okay. So now this is the solution to those equations? Is that right?
No. That's just an aside about delay differential equations that some people were using. And I was just pointing out that you have to be careful using them because you can get some non-physical effects, such as negative numbers of people.
Right. Right. Well, I mean, okay, fine. But so here, so I mean, just so I know some basics. I mean, if I look at the actual data that exists today from countries around the world, and I compare it to a model like this with some value of beta, some value of gamma, does it fit or not?
Sort of, more or less. If we had data for the disease where there was no intervention, then we would probably be able to fit it fairly well. But because there's been a lot of intervention, quarantine and things like that, the kinetics of that, of the real system, are not captured by such a simple model here. And that's the one thing I've been trying to work on, is try to find out what kind of model do you need to actually capture that.
Okay, so but do you think that the failure to capture is for these networky reasons, or do you think it's for the rate equation type reasons?
Since I'm trying to look at just a single quote unquote homogeneous population, just one province or state, it's probably more that we don't have the right topology of the model itself. That we don't have the right, we're not including the interventions in the right way. I've tried a few of them, and I'm working on some others right now to try to capture quarantine and isolation, which should have a significant effect on getting the right shape.
But do you think that that's modelable by? I mean, this is essentially a continuum model.
Yes, it is.
And do you think that so I mean, is quarantine modelable?
This type of model can also be recast as a stochastic problem, essentially using something like the Gillespie algorithm to get a trajectory, and that you could actually implement some of the containment strategies more naturally in terms of types of events and so on. And you might be able to get a better type of simulation.
So by stochastic, what you mean by that is you are imagining that your parameters here represent ensemble averages, and that's what you're.
And yes, you draw a random number from the right distribution to get what event's going to happen next. You do that event that, let's say, infects somebody, and then you draw from a different distribution for the time to wait till the next event, and then you choose the next event and do that. Maybe somebody gets infected again, or somebody recovers, and you just do that.
So actually, you say you're using a Petri net here, but Petri nets have, I mean, aren't necessarily differential equation stories.
No, this is just another way of describing it and showing the rates.
Okay.
So by the way, though, for what you were just describing, I mean, is it understood what a lot of those distributions are? Like, oh yes, the distribution of, let's say the time between infection and recovery is going to be approximately this kind of distribution, or
yeah, generally they're exponentials. Yeah, it's been a few years since I've worked on them, and I don't remember the details. I have to go back and look, but it's fairly standard. One I know is an exponential. I think the other's a beta, but I could be wrong.
Which is the, what do you mean the other, or did you mean models for the infection recovery time, or?
It's the same distribution. You just changed the rate constants for them. That is basically the time delay or the characteristic for the given distribution.
So you say when one gets sick with a typical random, I mean, is this true for all diseases, or is this, I mean, this is certainly not specific to this particular disease. So I mean, what you're talking about is you're saying that if I were to plot, what is the PDF of this thing? Am I completely confused here? Oh, what do I want to do here? PDF. Oh, that's not the X that I want. What do I want here? A parameter 1 or something? PDF of that exponential distribution, comma X, right? Okay. What is is it trivial? Is the PDF of an exponential distribution an exponential? Yes, it is. Okay. So are you telling me that something which I find implausible, to be perfectly honest, that people, let's say I get a cold, you're saying that the probability that I am still sick decreases exponentially with time. Is that right?
I believe that's right. And the rate constant that we use is the reciprocal of the average recovery time.
Does that really seem biologically convincing? Doesn't seem convincing to me. I mean, it seems like, isn't there a sort of a minimum time for the immune system to do its thing? I mean, if you started, I could even imagine writing down differential equations for the operation of the immune system and things like that. It just doesn't seem plausible that there would be a scale invariant distribution like that represent. I would expect there to be, most people are sick for at least 2 days with this thing, and then they steadily get better.
Yes, that's probably more realistic, but again, trying to model something like that is more challenging than just making the simpler assumption.
Right, but I mean, the question really that I have is what matters, right? Because looking at what we did up here, it's clear it really matters whether you're using distribution A or distribution B.
Mm-hmm.
And we can't immediately argue why one is better than the other. They each have certain characteristics.
Right.
I mean, this idea that I guess I hadn't really internalized, this essentially people chaos idea that's being used to make these continuum equations, seems really questionable to me. I mean, because it assumes that there will always be a ready supply of additional people to interact with, which particularly in these social distancing situations, that just seems exceptionally
well impossible. I guess that's why Bob was saying that these models are probably, it does, for example, in the real life situation right now, it probably doesn't exactly follow these models because there are a bunch of interventions like quarantines and social distancing that basically make it so that these don't necessarily capture what's going on.
Right. All right. Let's just get a sense though of I'm trying to get a sense of okay, so what is this?
That's just about optimizing parameters. So we scroll past that, but down here is where you start to look at some real data for an epidemic outbreak and what the model would be able to say about it.
Right. So this is from some flu data.
Yep.
Okay. So what? So if we look at the prediction of that model, it's going to be, I mean, it's just like radioactive species or chemicals or whatever else.
Mm-hmm. Mm-hmm. And we can model that fairly well.
Mm-hmm. So where's the okay, so this is a fit, but what does the actual most obvious model look like? Does it have it initially rises exponentially, and then eventually what dominates is your gamma term, and it decays?
Right. As the students recover and there are no more students to get sick, it decays.
Right. Okay.
And that's the other data set. And then if you scroll down a little bit further is where the fitting, we actually do the fitting.
Okay.
And there's a nice manipulate there, so you can.
Okay. So what is this showing? So this is showing. So beta is your force of infection or whatever.
Yeah.
Okay. So as we increase beta, this curve, what is R?
R is the recovered. That's the blue curve.
Okay. So who's sick here?
The red ones.
Okay. All right. So then as we increase beta, this gets steeper. Decrease beta, it flattens the curve, as they say. Okay. So then, okay. So this is an incubation period.
Right. So as it takes less time to get to become infectious, which means zeta is getting larger, the curve rises faster.
Wait a minute. As you increase the recovery time, why does that make?
As you increase no, that's not time. That's recovery rate.
Oh, I see. So increasing the recovery rate means people just get better quicker, and so
right.
Many people are sick.
Yep.
Okay. So that's okay. Okay, I understand. So then okay.
And those are the susceptible people, the healthy people.
Right. So in this model, basically everybody gets sick.
Indeed, and that's one of the problems with this particular model and these data, because not all the students did. Only about 2/3 got sick.
Why does one think that happens biologically?
That everybody gets sick, or
no,
not?
That not everybody gets sick.
Well, if you go back to the journal article about these data, the quote unquote infected students are really the students that were confined to bed. So they were not freely circulating, going to class, eating meals with their classmates, and were in a sense quarantined.
But so the other people didn't get sick because they were not exposed, or the other people didn't get
basically
sick?
Yeah, because they were mostly because they were not exposed.
As opposed to actually they were sick, but they weren't symptomatic, and nobody would know it because nobody went and measured, IG whatever levels.
That's another possibility as well. They didn't show symptoms, and some students just didn't report to the infirmary when they got sick, such as the older students.
Okay.
They were taking the opportunity, because classes were curtailed a bit, to just stay in their room.
Right.
And
okay, fair enough.
Yeah. So, you know what students are like.
Maybe. But okay. So let's see. So this is attempting to fit those parameters.
Well, the parameters have been fit, and this is just showing how if you change one of the parameters, how sensitive the model is to the parameters and where it's most sensitive. So this is basically saying that if we increase the infection rate, then the curve will shift toward the purple region, and if you decrease the infection rate, it will shift toward the yellow region.
Right. Okay, but so obviously these equations have existed for a long time. Yep. And presumably they have been tested on all kinds of epidemics.
Yes, and they work fairly well if you have a large enough group of people involved. And even for this small number here of only 800 students, they seem to do fairly well.
And to what extent, I mean, these various kind of social distancing, public health measures and so on, is there an expectation? I mean, have those been tried enough in the past that one would know whether these equations still work for those?
That I don't know.
Fair enough. I mean, I think okay,
but certainly a model like yours would be able to test that hypothesis.
Yes, I mean,
because you could certainly restrict the network how many the vertex degree, basically you're reducing it drastically.
right. But I mean, so what one could do, I mean, in this type of model, it takes only making this into a cellular automaton on a graph or something to have something where in some limit it should turn into one of these models, right?
Right. Yeah, I would basically build the first graph that's supposedly realistic of the social network and then remove a bunch of edges
Yeah.
to bring the average vertex degree down and see what that does to the spread.
Right. I understand. But I mean, what one should be able to do is okay, so what is the effective geometry of, in your model, what is the effective graph that your model is using? The effective graph is something where it's some kind of
It's
graph,
assuming a complete graph. Yes, indeed.
Okay.
But so actually, one way to think about it is you have an underlying social network graph, and then for each vertex, you have sort of a distribution that tells you how many neighbors of this vertex is this vertex going to visit, right, or is it going to interact with, and then basically that's how you actually get transmission. And so the idea is that when you say you have a complete graph, then you'd expect that, okay, if you have one infected agent, then all of the agents are going to be infected the next step. But so you sort of need that extra modeling step that basically each agent doesn't meet with everyone else that it's connected to, but it only
right
meets
in
some
the next
number,
time step. You're not going to visit everybody, but you would randomly, some number would be likely to be visited.
Right. So
yeah,
the other
exactly.
assumption is continuous time. Yeah. In your thing here, and continuous time is, I mean, that seems like an okay assumption. I mean, it's not like, I mean, there is in fact it is in fact episodic in the real world because people are likely to meet more people during the day than at night and things like that.
Mm-hmm.
So it isn't in fact the case that there's continuous time. But I would suspect that that's not the most important assumption. But okay, so I mean, in these models, if I'm understanding correctly, this curve doesn't start going down until a large fraction of people are infected. Is that a true statement?
So far, that's that from what I've seen, certainly for these data and these models, that's the case. And for the second data set, only a third of the student body got sick. And it wasn't until I included a quarantine in the model that I was able to get something close to that.
But so quarantine, what were you doing with quarantine? Were you just taking people
out of the infected.
That's
right there. The infected people could either recover on their own or they would be quarantined and then recover from there. And if they were quarantined, they were not able to infect other people. So the total force of infection was reduced.
Right. So I'm seeing here there's what you've got is, I should make it bigger for people. Let's see, you've got a minus quarantine. What's Q prime? Q is the number of
quarantine people, and at some rate, the rate delta, the infected people become quarantined. So reducing the number of infected people able to infect others.
I see. So that's the quarantining.
Mm-hmm. So that's reducing I, and that reduces the overall infectiousness, of the system.
Wait a minute. So where do I want to go here? So if I say here, so you're saying increasing Q. Do I have a parameter here? Is that your delta parameter?
That would be the delta, yeah. So as you move more people.
So at low quarantine levels, lots of people are getting sick here. But why is anybody being quarantined there? I don't understand that. That's a delta That's a parameter delta, which I'm setting to
Right.
be.
It's not zero.
It's not zero.
No,
okay.
these are on a log scale, so they're more manageable, and there's a lower bound. I forget where I set it, but it wasn't zero.
Okay, so in this case, this is sort of the situation that we're in right now, is tons of people are quarantined. Although that peak quarantine in your case here is happening later than the peak of number of people infected, which is kind of weird. Right? I mean, one would expect
I see that, yeah.
That seems kind of weird.
Well, it's a combination of the other parameters as well that have an effect on that. So,
right. Oops. But we're still seeing, it's like, why are these people bothered to quarantine? Well, maybe it's important, because.
Well, you have to be sick before you get quarantined. There's another model where you can quarantine directly off the susceptible compartment.
Right. Well, in that case,
what we're doing.
Right.
Yeah.
Well, in that case, it's obvious you're going to reduce your beta by by the amount of. I mean, as you take people out of circulation, you're going to, in this equation, wherever it is, where is the?
Yeah, it would be the S equation there, the last one. You would be reducing the number of susceptible people.
Oh, I see. You're effectively, so it will be an S minus your preemptive quarantine.
Right.
Okay, which we could presumably solve here if we wanted to. Okay, but actually we've got a whole bunch of comments on the live stream that I haven't been paying attention to. Let's see. Let's see. Talking about social distancing. Yeah, that's interesting. BTC Fly is pointing out that premature restoration of social interaction would lead to oscillatory behavior, and that's something that we could presumably model here. If we explicitly put in a something that preemptively quarantines, what we will presumably see is that as people return to the pool of susceptible people, you'll see this go back up again, and this will oscillate. Right. So in other
words, if they return too quickly.
Yep. Right. So I mean, the optimal thing, if we were doing control theory here, what we would be doing is we'd have, I don't really know these things well, whatever it is, the PID controller or whatever it is, some kind of control system that attempts to, if we were able to have that level of control, to sort of titrate the level of social distancing to do something to this peak, right? Because clearly, if you just bring everything back, if that had been going down, it's just going to go back up again with a time delay because of the time to which presumably you are modeling here. Are you modeling it with a delay here?
No, I'm not using delays because of the oscillations that they induce in the model and the risk of running negative.
Yeah, which is kind of a big red flag about something might not be okay with the model. But so let's talk about that. I mean, you had examples up above of delay differential equations and their pathologies. But so why are those pathologies happening, and are they actually telling one something about the science of what's going on?
To be honest, I've known about delay differential equations for ages. I've never really started playing with them until last week. So,
I mean, okay. We have a bunch of experts at the company in delay differential equations.
Yeah, but why they induce oscillations, I don't know. It's interesting that such a simple change can do that.
No, I'm not super surprised. I mean, I'm sure that these equations, you can quite easily get chaotic behavior in these equations, I'm sure.
Yes.
And
sometimes the DDEs are invoked to try to capture that's observed biologically with some diseases, where you end up getting periodic behavior that's sort of seasonal but not quite. Measles is a problem like that.
But like the Lotka-Volterra equations, they are. I mean, that's pure predator-prey stuff. But is that those map onto some epidemiological things, as I recall?
They're very similar, yes, and you can get systems set up so that they do that. You end up with a limit cycle.
Right. Or actual chaotic behavior for some parameter values.
Yes. And some diseases behave like that. Measles is one. And we've done modeling with other diseases where if you end up in the wrong part of parameter space, you end up with very chaotic behavior.
Which leads to what? Which leads to nobody knows why. I mean, it leads to sort of chaotically varying numbers of people sick and things.
Exactly. You get these outbreaks. You get long periods of time where where nobody's sick, and then you get a sudden spike that rises quickly and then decays away again. And even with vaccine treatment, you can see that happening.
Yeah, someone's pointing out on the live stream that System Modeler would be a good thing to use for this. That is a perfectly good point. Have you tried looking at that, Bob?
We did a pilot with a client to use System Modeler as an interface for these epidemiological models, but I haven't used it myself, mostly because we've been using age-structured models, and it's much harder to set those up with System Modeler because you've got an equation for each compartment for each age group. But what you were just saying before about using some controllers, that would be I was thinking System Modeler would be a natural because they've got all these controllers built in. It would be a nice way to try that.
Yeah, I mean, we've actually got pretty decent control system stuff right in the language, but I don't think. I mean, I think that's I think that's a higher order issue. I mean, if one doesn't have the basic model working, so I'm curious. People on the live stream are talking about graphical models. I'm curious whether people have used those actually for this, where you have these probabilistic networks and so on.
I've not seen it for these sorts of things.
I mean, the things I tend to hear about are the differential equations and the networks, and those are the two types of modeling that. So yeah, so the comments here about the generalized logistic model predicting things that are actually observed here. Let's see. Yeah. So tell me about I mean, these generalized logistic models. These are what is the idea there?
I believe they're mostly just looking at the trying to model the number of the cumulative number of infected people.
Okay.
Which you would expect to rise exponentially and then flatten out.
Like a logistic curve.
Yes, exactly.
Okay.
And that's essentially modeling the cumulative incidence, which you can calculate from the differential equation solution. The differential equations solutions give you the prevalence of the disease, how many people are sick at a given moment in time.
Yeah, you just take the integral up to that point, and
more or less.
Okay. Well, so the question, I mean, okay, so coming back to how do you make these models? I mean, so for example, there's presumably an interaction between geography, physical, spatial geography, so to speak, and I mean, if in a city, more people are there's more people to interact than there are not in a city. So there's presumably some interaction, not only of these networks in social space, so to speak, but also in physical space. And one wonders whether that variation is important. Does one know for the current epidemic data, does one know whether the number of people sick is proportionately more in cities than not in cities, for example? Anybody know that?
I don't know if we have data at that level of detail.
No, I don't think we do. I mean,
yeah,
I think
exactly.
Is there something we can look at here? If we start, well, let's see. So I mean, I mean, do we believe? Okay, so there are various assumptions that are being made. I mean, so there are various questions like, is the quote social network, spatially invariant? To which the answer is undoubtedly no. Right? And does that matter? Does the homogeneity of the social network matter?
Well, there's also questions about like, are there local effects where, for instance, if you have a non-homogeneous social network, then do certain vertices end up having a higher probability of being infected than others, and so on.
Right. Okay, so I mean, because a lot of these models, even if we're doing social network models, the most obvious way to do that modeling is going to say this network, every node is equivalent to every other node here.
And we know that's not true.
Right. Fair enough. So I mean, what other questions? I mean, they're questions of I think perhaps the most interesting thing is the what matters question. Which aspects, I mean, because what we saw here was between these two networks, it mattered which network you chose. It wasn't enough just to know the mean degree distribution. Did you figure out, Christopher, you were talking about some other possible things that might matter and not matter. Did you figure out any other
well, okay. I mean, I guess so. Right. I mean, it matters what the underlying social network is, and it also matters what the average degree distribution is, and then it also matters, if you're doing this thing that we were talking about earlier about how if for each vertex you basically pick some number of its neighbors, and it's going to visit that number of neighbors. If you talk about what the distribution is that determines how many neighbors you're visiting at each step, then that distribution matters. And the mean matters, but also things like the standard deviation and the skew and things matter. So it's sort of, a lot of the details of that distribution matter.
Right. I mean, that has to have an effect on, on policy kinds of questions, because, once one knows what matters, one has a better chance of figuring out. I mean, clearly, well, if one can shut down anything that could possibly matter, then one successfully shut things down. But I suspect one of the issues that's going to come up is, to what extent can things be reopened and when, and what can you reopen, and what matters more, to have large numbers of small gatherings of people or small numbers of large gatherings of people, for example. Is that a thing one could imagine answering? I mean,
probably,
but not with the differential equation model, right? Because, or maybe one could. Maybe there's a driving term there that.
No, not really. Not unless you break up your the S compartment into a number of S compartments that would represent small groups and big groups or something like that. So you would be able to, have different effects on them. They would interact differently.
Boy, this is a complicated modeling problem.
It is. But I really like the one that you were doing with the networks, because it seems to be more realistic. It's more tangible to what we know from normal day-to-day life. And if one
those
could
networks
find,
aren't that realistic, unfortunately.
But if we could find a contact network that was more reasonable, that was more similar to what people actually.
I know people have. I mean, people have at least done sort of trials in various cities of various kinds of track everybody type things, and there must be data from that on. I don't know whether there are any. Christopher, I think you were looking at some for some data sets of that type. Did you find any good?
Yeah, well, I mean, the difficulty is that most. Okay, so there, as far as I can tell, there are basically two categories of real world social network data sets. They're the ones that are they're the ones that people did like before 2000, which are mostly just they're like surveys and things like that, where they ask people, who are your friends and stuff like that. And they're usually very small. And then they're usually also not terribly reliable because people have very different standards about what they answer for, who they're connected to. And then for the ones that are sort of the more recent ones, they're basically all online, some sort of, email networks or social, online social networks. And these are two kind of issues. The first is that often the degrees are crazy. Like, for example, if you look at the network of Facebook friends, the average degree is like hundreds, which is kind of unrealistic for sort of person-to-person contact. And the same goes for things like email. And the final problem is that a lot of these social networks are also really big, which at some level is realistic, but not super useful for modeling. Because if I give you, the social network of, all of Facebook or some giant email network, and it's got, millions of nodes, it's kind of hard to run a model on that. But in some sense, that aspect is kind of realistic. So it's kind of difficult. I mean, most of the things I found basically try and use these two graph distributions here, which you can kind of alternate by, because you do know that, for example, the clustering is pretty realistic on the Watt-Strogatz one, and that the Barabasi Albert one has realistic degree distribution. And so depending on what you're doing, you can kind of alternate, but it is sort of sketchy.
So I'm curious about a few things. So I mean, this is our old data from Facebook, which we've never we actually have a lot of data which we stored in anonymized form, and we've only sort of published microscopic pieces of it. But you think that this is not? This is number of friends versus age, and this is like the 20-year-olds have 400 friends, which is probably not realistic.
Yeah.
I do wonder whether this is, for example, I wonder whether, in terms of the infection rate as a function of age, I wonder whether there is in fact a sociological phenomenon of number of friends.
There is, and there are what are called mixing matrices or contact matrices that epidemiologists use that tell you the number of daily contacts of people in one age group with people of another age group.
Right, but this is saying, at least in the case of Facebook, at least in 2013, the average number of friends decreased with age quite dramatically here.
Well, but that's
probably computer use.
Yeah, exactly. I mean, if you look later,
no, but that's the number of friends.
Blog,
well, okay.
Yeah, if you look later in the same blog, yes, that right there.
Or that's a good plot, right?
Yes. So basically, it tells you that if you move that slider there, it tells you that basically most people are friends with people of their same age, except for old people who are also friends with their children and grandchildren. And things like that.
The assortativity. Yeah,
and basically, if you're mostly friends with people who are your age, but there are fewer people of your age group who are using Facebook, then of course you're going to have fewer friends.
Fair point. Right. So okay. So this is, in terms of data, we actually have quite a lot of data that which we could try. But you think it's useless. The fact that we have all of this data on all these networks from Facebook users in 2013.
There are two issues. There's one, the fact that the degrees are all too high, and then second, the fact that, well, my impression about this particular data set is that it's not, you don't have that much, you don't have too many cases of you have two people who you have data from and their kind of networks intersect in a nice way, right? You don't have like a dense.
I don't think we studied that. I don't think we studied that well.
Okay, well that's a question. But then the other thing is that even if you had only the social network around one person, right, going two levels outward, you already have plenty big network, right? Mm-hmm. You already have tens of thousands of vertices probably,
yes.
or at least thousands, and so that's already big enough. But then again, it's the problem of the structure of this network is kind of weird because it's all just sort of this radial network out from this one person, and the degree distributions are totally bizarre.
Right. Hey, you looked at that Singapore network data, yeah? Do you have it?
Yeah.
Do you have it? Could we bring it up and just do you have
the please hold. Let me see. Yeah.
you want to share your screen, or do you want to send it to me? Or
sure, I guess I can. I'll send you. I can send you a few lines of code if you don't mind.
Fine.
Okay, let me see it.
Fine.
Should I do it over? I'll do it over Rocket Chat. So there's the first. So this is from this. This is from this this project website. I don't remember exactly what it's called.
I'm not seeing this. I think you're sending a different channel. Why don't you send it?
Oh,
that was Zoom chat.
Okay, I can send it over. I'll send it over Zoom chat. Those are three lines of code.
Where am I getting the raw data from?
From a website,
Yeah,
which eventually gets it from. I can. Oh, wait. Sorry, one of the links I sent you is wrong. Or one of the lines of code I sent was wrong. The first one is actually this instead of the ArcGIS thing.
So that's a Singaporean website, and what I should not use this. I should use this instead.
Yeah,
get the raw
that
graph.
should work unless they've changed the structure of their website in the last 2 days or so.
Okay, see what happens. Wowee!
There you go.
Really?
So by the way, this graph. So there are a few things to note about this graph. So first of all, this graph is there's two types of vertices. It's got like people, it's got cases, which are people, and it's got clusters, which are like the such and such conference. And a lot of these high degree vertices are clusters.
I see, not individual people.
Yeah. So I mean, because they don't know. I mean, if it's a bunch of people went to this conference and a bunch of people came out sick, it's like you don't know who spread it to exactly who.
Okay, so what this is their best effort to track cases where this particular person gave it to that person there. It's a directed graph. Is that right?
Although I should also mention one other thing, which is the way that these people curated it is that the Singaporean Health Ministry every day, I think, publishes this thing where it says, case number, there are now 5 new cases, and case number 312 is a family member of case number 250, and then they draw an edge on this graph.
Okay.
So there isn't necessarily a causal thing, but
does this mean that so in Singapore, where they've done really good job of tracking cases and so on, those isolated nodes down there. So if I say for this thing, I say connected graph components, what I'm going to see here is if I
it's a directed graph, so you're probably going to get a bunch of silly stuff. But
okay, so let me undirect it.
Maybe weekly. Yeah.
Yeah. Okay. Can I do that? Weekly connected graph components? Yeah. Yes. Weekly connected graph components. Okay. So what I should see here, is all right. Lots of individuals where they don't know where it came from, right? And others where what we're seeing is, which is quite interesting. This is showing all the sort of clusters of known infection. So like that person gave it to 2 people, and then that was stopped somehow. This will be a case where one person gave it to, well, we can work out the degrees here, right? So I mean that in that particular case, and you say you don't know if it's a person or an event, but that was a degree 5 or something.
Well, you can also see though that a lot of the people, they don't know who they got it from because they had contact with multiple people.
Right.
What do you mean by that? So you mean that
look at the bottom vertex here. It's got 4 edges going into it. Presumably you don't need to meet 4 people to become infected. Yeah.
I see. So there should be in degree 1 for every vertex. In
principle. Right. In principle, it should be a tree. It's actually a DAG.
Yeah. Well, wait a minute. Wait a minute. Why is it a tree? Because you're saying every person should have 1 predecessor and multiple successors. Yeah. Okay. Fair enough.
Yep.
And there shouldn't be any loops.
But I see. So how does that relate to? Okay, so let's compare this to, for example, if we go back up here and we look at this neighborhood graph here. If I say, I mean, okay, so let's
that's
compare.
That's going to be a DAG as well, but.
Yeah, and it's probably going to be weakly completely connected.
All right, so let's look at the two-level.
Note that also this is an undirected graph, while the other one is directed, but. Right,
okay,
I mean,
so it's just a total mess. So that thing had a ridiculously high degree.
So yeah, maybe pick a different vertex, because I think you just got really lucky in that vertex number 1. Actually, okay, wait. Actually, can you do this?
Let's try.
I think that your previous exponential thing was actually wrong, because try running this. Just run vertex degree of BGR.
Yeah.
Because I think it actually sorts the vertices by degree.
Oh, that's terrible.
So you're being very unfair by starting with degree 1.
Yeah.
But just check
by
vertex, just run
1.
vertex degree of vertex degree of BGR. Yeah. And I think
you are correct. Well, no, you're not entirely correct.
It's approximately, yeah.
There are high degree
you want to pick
at the beginning.
You want to pick a random one. I think this is a structural thing. It'll always have high degree vertices at the beginning. So you want to pick a random one.
Probably from the way it's constructed as well.
Okay, fine. So let's go back up here.
Actually, I think you know why it's like that is because it starts with a small graph and then it adds vertices and adds random edges back into the graph.
All right. So
if you have a vertex that's been there for a long time, it's going to have lots of opportunity.
Someone on the live stream is suggesting that we actually take a mean over multiple vertices, but let's at least do a random sample of a vertex list of BGR, and let's say we just do let's just get 5 of them, for example.
Yeah.
And there, okay, so there's our random things, and now here we want to say, let's see, for each of these we want vertex count. Let's take the mean of the vertex count. What am I doing? I'm doing this.
Well, I would suggest doing the mean outside. I would drop the mean for now and then put the map outside of the table so you can first see how reliable they are. And then you can take the mean afterward.
Okay, fair enough. Okay.
But I mean, this is one of these things where I guess it's probably somewhat realistic in that it's one of these that the initial conditions are very important. If you start with this, this vertex being the infected one, then you'll get a very different answer than if this other one is the infected one. But
right. Okay, so there we go. So now let's look at those. Let's log plot that, join true. Okay.
I mean, they're also pretty steep.
They're all steep, but they're all slightly different.
Yeah.
Mm-hmm.
And presumably, if we were to take the distribution, we could get, for each of these, we could get a distribution. So for every value of t, we can be computing a distribution. So let's actually do that just for fun. Just look at the distribution, depending on who we start with, at how different the number of people who are sick at a particular point. So what that would be is something like where we are looking at over, let's take a random sample of, let's say, 100 of these. But let's do that inside here. And then for each of these, let's make a histogram. And let's say we only do that up to 10 steps because I don't think it's going to be very interesting beyond that. Let's just see what that looks like. So that should be 10 histograms, each for 100. And I should make use of the fact that I have a network of 100 computers here. Hold on a second, let's do that. Let's use parallel map here.
You should use parallel table. You should use parallel table, not parallel map. It's coarser. I mean, it'll be 10 times as fast, but.
Well, okay, fair enough. 10 times we'll take 10 times. Oh gosh, now it's going to launch all these crazy computers. Okay,
well,
nice.
This is the reason why maybe maybe you should abort this and instead just write launch kernel 10 and then run it and then say close kernel. That might be a bit safer than just sitting around and.
Well, not all the machines are quite as fast. The one I'm actually sitting at is faster than the other ones.
Well, right. I think You should run. Oh,
okay, we got the answer. It took almost no time after we'd launched all the computers. It took no time to actually get the results. Okay, so what this is showing is the distribution of the number of people who get sick depending on who we started with. There's some weird behavior here.
Some of the weird behavior is because it's hitting the ceiling very fast in some of them and not in others.
That may be true, right? But I mean, I think so here, let's just try if we have like 500 samples there, let's just see whether that makes a difference to what we see. But this says it really matters. I mean, it's kind of interesting with respect to what one knows about what happened in Italy, for instance. I mean, it seems to really matter where you start from in the network, right? Because this is, these distributions are quite broad. It's
I mean, this is like the thing where, right? I mean, if you have exponential growth and you change the initial state by a little bit, it changes it by a lot.
Well, except that the exponential growth, you would expect that the thing is expanding, exponentially into the bulk, you might call it, of okay, but so what do we learn? Let's see. I have some questions on the live stream here. Someone's asking Bob, are there publicly available mixing matrices?
Yes, there are two publications. The more recent one, the first author's name is Prem, P-R-E-M. And they've got matrices, 3 different kinds. They've got all locations, at work locations and at home locations. And they've got them for most of the countries in the world. It's a bunch of Excel spreadsheets in the supplemental information. The earlier work is by Massong, M-A-S-S-O-N-G. There it's I think just for a handful of countries in Europe.
So actually, a question about that. Do you know if they also have the distribution of, for forgetting about age or anything like that, do they have the distribution of, given a person, how many people do they interact with, period, regardless of age?
That I don't know. I do know that these were collected from survey data, so they're somewhat realistic.
Okay.
Yep, it looks like the Prem paper. Yeah.
The next picture looked like a matrix. Oh.
Huh.
Yep. And you can see that there's a lot of assortativity, that people tend to mix with people of their own age. That's the main diagonal. But then in the one on the top right, you can see that 30-year-olds tend to interact with a lot of people that are around 10 years old. So that's probably parents interacting with their children. And then on the opposite side of the diagonal, you have the other group there where you've got, well, depending on how you read it, then this would be adults interacting with children.
Yeah, right. Which should be symmetric, shouldn't it?
No, it's not symmetric. Partly because of the way the surveys were conducted. So someone would hand you a survey, Stephen, and you would write down everybody, the ages of the people you interacted with on a given day, every day of the week. But we don't have the interactions of those people who interacted with you along with others. So the data collection was not symmetric.
Right. It's similar to the friend paradox type thing, where you end up with everybody has some, what is it? Everybody has an above average number of friends or something? I've forgotten.
No, on average, you have fewer friends than your friends.
Oh, okay. Okay, let's see. We got some other questions here. So far, I've only seen parametric bootstrapping for deriving uncertainty measures. Do you have any better ways to do this? Especially for the ODE models in which variational Bayes framework surely becomes stochastic differential equations. Interesting. Work on differentiable cellular automata and neural cellular automata. Yeah, I'm aware of some of that.
Yeah, I mean, one of my tech conference presentations was recorded where I did do this stochastic modeling. It wasn't stochastic differential equations. It was basically doing the Gillespie algorithm.
Which does what?
It uses the same information that's in the differential equations, but it's where you draw from an appropriate distribution what's the next event going to be, and then you wait a certain period of time, again drawn from an appropriate distribution, before you choose another event. And these distributions evolve over time as well. And this is where I was doing the in-host modeling of hepatitis C virus infection, of how many viral particles are within an individual.
Right.
And there you can start out initially when somebody's infected, you've got millions and millions and millions of viral particles within the person, and these differential equation models are okay. But as soon as you start getting down to near the limit of detection, you still have a large number of viruses within the person, but it's a countable number. And then we would switch over and do the stochastic modeling to try to estimate the time to cure.
So how many virus particles does it typically take to make one sick?
That I don't know. Usually, I mean, once they are initially infected.
Yeah, I mean, like if I, if I touch something and it has viruses on it, how many viruses do I have to, put on myself to?
I'm sure studies have been done, but I don't know what it is.
But I mean, you're talking about the point where you can no longer use continuum modeling, and my impression was it's like millions of virus particles that you need to get to.
That's where we switch over. The limit of detection is like 10 ppm or something like that. But
limit of detection of what? Of
virus in the blood. So they would draw you get, when you get tested to see whether or not you've got hepatitis C, they draw blood and they do an ELISA assay to see the antibodies against it, and the limit of detection on that cuts off at something like where you still got something like 10 million viral particles still floating around. You just can't count them. You can't detect them because it's too low. They're too diluted.
In these swabs that everybody's giving for the PCR detection of the COVID stuff, what is the I mean, is that at the limit of detection, or is that?
There's a limit of detection on that as well, but.
But is it close? I mean, is it like it might be PCRing up the wrong thing, and so it will get the wrong answer, or is it like it's not close at all? It's that like there are tons of virus particles there.
Being undetectable is not necessarily being cured or not being infected, and I don't know what the limit of detection is, and it's a very valid question.
Okay, but anyway, yeah, go ahead. Sorry.
For hepatitis C, what we were doing is typically what they used to do is you had to be undetectable for 12 weeks after treatment stopped. That would, and then you would be declared cured. And what we were trying to do is do the modeling so that we would have a better idea of how long you had to wait, based on what the distribution was of times to cure.
So in your model up here, you actually had a parameter, which is the one of your parameters here is your recovery parameter gamma or something.
Yeah.
Yeah. And that's, I mean, but and so is it the case when you go from here to here that the number of viruses, I mean,
no, this is a population model.
That's population, but right. we could also be modeling the viruses, presumably.
Right, the viruses in the people's within their blood, right, that are moving around, and at some point
is getting rid of them,
treating them with some medication, for example.
Mm-hmm.
And or if you were in the hospital and your clinical symptoms go away, but the assay still says you've got virus in you, so we're going to keep you around for another 2 days or a week. I believe the WHO has recommendations. I think it's 2 weeks that you have to be symptom free before you're declared recovered.
Right.
Something
Hey,
like that.
I was trying to estimate something. Maybe you know how to do this. I was trying to estimate how many copies of this virus there right now are in the world.
Within an individual?
No, just in the world. I mean, like there's on the order of 7 times 10 to the 9 humans, and I just wondered how many viruses there were. And first estimate puts it around 10 to the 20th. I just wondered if
it's almost a mole.
Yeah, right. It's some. It's just to get a sense of what's involved. So let's see. The just coming back to that. Okay, so the thing we're realizing here is it really matters in these networks. There's a lot of inhomogeneity, and it really matters where the seeding point was, which is quite interesting.
Mm-hmm.
And as people on the live stream have been mentioning, computational reducibility, which of course is not far from my mind. Of can you in fact compute? Can you in fact predict this at all? And the one thing to remember about computational reducibility is that whenever it's there are always collections of pockets of computational reducibility, and it's worth looking for those. And so it might be that there are things you can compute, even though the whole story might be sort of an irreducible to compute thing. But I want to come back to the Singaporean data, because this is really cool. And I don't think there's any such data from anywhere else in the world of contact tracing and so on. And I just wonder whether what can we learn from this network?
I mean, it's kind of difficult because, again, you only have the edges that have infected people at both ends, right? You don't have the
okay, so here's
network.
One thing that I might conclude. I mean, what are these you say might be events, but what I'm not seeing is that everybody has high degree, it's
high
not the
out
case
degree.
that most people have quite low out degree.
And that's because these networks are being traced backwards generally. And you trace backwards and you find somebody infected, and then you have to start tracing forward from there to find the others. And I don't know, I have no idea how much they do that.
I think they have been doing some of that. But I mean, this, what you might expect to see here is, and who knows what that was, and that was probably an event, not a person. Is there labeling of this data set, Christopher?
The only labeling is for the cases, they're just numbered. And for the clusters, I think there are, they say like the something rather conference or the.
But then can we get that from the JSON here? Can we get that?
I don't think it's in there. Although actually you could look, it might be. It might be.
Look at the raw graph here.
Actually, I believe it is. The information about the clusters.
Okay, well, let's see which one is a cluster.
So it's under nodes.
Okay, so I want to take. Great.
You may also want to, when you import it, arguably you want to use UTF-8 because it's, I think. Okay, but
okay, so
yeah, so you have the IDs are the vertex names.
Okay, so we let's label the vertex names here. Let's draw this picture labeling the vertex names. Can you help me with the code here?
Just say graph of G, comma, the vertex labels goes to quotes name.
Okay, so let's get this. Really? That's all I have to do?
Yeah.
Quotes name like that, or quotes name with a lowercase?
Quotes name like that. That's correct.
Oh, wowee. Okay, well, that's the answer to whether that tells us which thing is a case and which thing is a cluster.
Yeah, I mean, you might also you could do this if you say vertex list of G,
yeah,
and then just say select.
delete. Yeah.
Well, you can vertex delete, but the easier thing is just do this: select the ones that match the string pattern cluster star, right? And then just do highlight graph.
Okay. What do I want? You want the cluster or the case? Cluster, you say.
Clusters, let's say.
Okay. Highlight graph of G, and then I just do that. Is that right? You think that's right?
Yes.
Okay, there we go. All right, so those are the clusters, and everybody else is an individual case. All right, so then let's get the in and out degree distributions for the actual cases. Okay, so that was a cluster. These big sort of explosions were clusters.
You can see there are also a few cases at the bottom in particular where, actually,
well, look, there's a complete
in a lot
graph.
of these places. Well, right, but it's actually just the complete graph because they all interacted at that cluster. I mean, you can see there are clusters that have no in degree, so it's just who knows who the original person was.
Yeah, I understand. But so, let's see. So here, if we...
So you should make a variable. So just why don't you do this? Make a variable that is the list of clusters, which you generated up above. Just say clusters equals.
Yeah. Okay.
And then just say vertex delete. And then look at the degree distributions.
Yeah, okay, fine.
Why don't you look at the out distribution?
Okay, so you say vertex delete of G and then clusters, and that should give us the graph without the clusters.
Yeah.
Okay. So those are all individual, and now take that. Okay, so that's actually kind of interesting in its own.
There's only one subtlety to this, which is that in the few cases of clusters where you do know who brought the disease to the cluster, it's not treating it as if that person spread it to a bunch of other people, if you understand what I mean.
Yeah, I understand what you mean. But I think that's a minor issue here. So, okay, so what are you proposing? You're saying...
Checks out degree.
Of
that vertex delete.
And then you say make a histogram of those.
Yeah, so this is basically saying how many people is it known, how many people does each person directly infect?
Well, that's interesting. I mean, that looks like some kind of exponential thing. Let's just get the actual, let's just ask for the counts here.
I want to say key sort.
But what the heck does this mean? The out degree. So these are people, I see, because this is what Bob was saying about backward tracing, that these are people who got sick, but it's not known, but they don't, the vast majority of people, they got sick, but it is not known that they passed it on to anybody else.
Or they don't know who they got it from. Are those all the singletons?
Well, no. So this is only the out degree.
So this is the out
degree. Everyone should have a yeah.
If we look at the in degree,
that's right. Yeah, that's right. Yeah, the out degree is who they would give it to. Yeah.
Oh, but there are a lot of in degree 0, which are the mysterious, who knows who they got it from.
The singletons, yeah.
Well, it's not just singletons. It's also things like, you know, there's that one, if you look at the cluster that's, I can't really point, it's like it's pointing to a constellation. There's a cluster of like 5. That's.
Oh yeah, this thing here, the pentagon thing.
No, up above, directly up, one more. There you go. That one has, no, below there. That one has a few has a few which have no in degree.
Right. But okay,
also, you
so
can see there's some weird multi-graph stuff going on up above.
That's just weird. That looks like a data error, or possibly.
I assume that's because the edges are all annotated. So like some of the edges are annotated family member, and others are annotated close contact. And I'm guessing it means it's both.
Yeah, and I mean, there's weird stuff here. Like there's something that gives it. Now it's possible. Yeah, right. They give it to them, and they give it back to them. Okay, but let's try to understand what we can get from this. So if we ignore the cases where the out degree is 0, this might be telling us what the degree distribution, what the effective degree distribution is on one of these graphs, right? So,
although again, it's also it's missing the fact that the number of cases is increasing and stuff like that. So it's going to be skewed low potentially. Like if you so if you imagined that that each of the people we're talking about is still spreading the disease and that they weren't perfectly quarantined or something like that, then it would be skewed low because the people who are marked as 1 still have the opportunity to spread more.
Yeah, I get it. But I mean, let's just look at this distribution in its own right, because that I mean, I can't really tell here, but that
why don't you can do ratios, you can do fit distribution, or
okay, well let's just do
why don't you just delete before you run counts, why don't you just delete the zeros?
Yeah, right. Oh, I could do that, but I was just going to do this, where I just do ratios of that because it's not going to make any difference.
No, it's kind of hard because there's so few of them.
Yeah, hard to really conclude much. But it is mildly interesting. There's a factor of 5 in 3 of the cases here. I don't know what that means, though.
Also a factor of 2 in 2 of the cases.
Well, except that last one is really irrelevant. That's down in the noise.
It's a full house.
What?
In a poker hand, if you have 3 of one thing and 2 of another, it's a full house.
Okay.
Whatever.
Okay. Well, let's see. What else can we figure out here? I mean, I think our original goal was to make, and maybe Rory, who's been quite silent here, might have been able to. What I was hoping to do was to get from this sort of an elementary treatment of what one can figure out about epidemiology suitable for people who are trying to explain it to students and things like that. I actually think we do have a bunch of that here, although it's a little bit sort of scary that these these models are quite iffy from my point of view in terms of but I mean, is there anything we can conclude if we actually look at data on the actual epidemics? Let's just pull in one of them. Where is it? I had it somewhere up here, way up here. I was closed it in the notebook because I didn't.
I remember you doing something with WDR there.
Yes. I can redo it. What was it? No. There we go. Okay. Let me just move that down, and so I can work on it somewhere else here. Okay. So in this case, let me pick for each. So the one question would be, if you take the time series. Gosh, why is this so slow to scroll? Probably because there's an awful lot of data here. So what do we want? We want confirmed cases, for example, for a and I suppose if we just take
If you want to see the number of people that are sick at a given time, it would be confirmed minus recovered minus deaths.
Yeah, but well, let's just take confirmed cases to begin with.
Okay.
And then this is going to give us hopefully
Something like the logistic curve.
Yes. Why is this taking forever here? Okay.
By the way, though, I mean it's. I never understood how this works because it seems like it breaks it up at different levels. Because in some places you have the entire country of Italy, and in other places you have the province of whatever.
Yep.
But I assume that there's no double counting. That if it says province of whatever, it doesn't have all of the actual country.
Oh, I don't know. I don't really know. I mean,
when I looked before, it seemed that was the case, but I'm not sure if that's correct.
I'm pretty sure that's right. The country will have all of the states' data, but each state, there's no overlap with the others.
All right,
but like if they list New York State, they don't list the United States, I don't think. I could be wrong.
No, they'll list the United States also.
Oh, okay. So some countries are double counted.
Oh, okay. Yes, if you want to look at all the data, then there will be double counting. Yes.
Okay, yeah.
But for each of those two, there's an administrative division field and a country field, and only one of them should have a value for any given row in the data set.
All right. So this is a random example. I mean, we could probably just for fun, although it will have some double counting. I just wonder what this looks like. That's going to take all of the various data sets. Oh my gosh!
You might say plot range goes to all, and you might also say total.
Well, okay, but I was wanting to look at it with come on! I just want to close up these. So this is presumably going to be dominated
by the China one.
That is so weird. Really doing that?
Yes, they've leveled off for the most part.
And that's why a lot of these models are sort of difficult, because there are a bunch of weird interventions which are enacted at weird times and etc.
Yeah, and that big jump in the China one.
No, I know.
Right there,
they changed data. They changed their measurement.
Right. Yeah, there was a change in measurement, and they suddenly had several 100,000 new confirmed cases. Yeah, there was 13,000 new confirmed cases on one day.
But so if we were to try to, it's not clear whether it's an exponential, whether it's something else. Hard to know. I mean, it would be nice. Is there some way that we could plot everything on top of each other to see to what extent these different countries, in other words, we'll have to shift them, right? Because they had different seed times.
Yes. Probably taking the first point that's not 0 and aligning those.
Well, so actually what I've seen a lot of places do is they do similar. They just align them once it's above 100.
Okay. Well, so how do I do that here? So I say let's say %175 sub 10 or something. Let's just pick a random example, a time series. Now, how do I do that?
I think you could say
if you just stick that into normal, you'll get pairs of numbers.
Yeah, I realized that. But then and then what are you suggesting that I just do first case of the
first position? Yeah.
Well, first position of
actually we could I was thinking we could use a replace, basically delete all of the initial cases where the second value was 0 or below a threshold.
Well, that's a good idea, actually.
And then the residue would be the ones afterwards.
And so you should actually say %180 of values instead of normal, because you want to get rid of the dates.
What are you suggesting?
Well, we know
Okay,
that
so-
the
Oh, I see.
data,
I see what you're saying. You just
Yeah.
want to, since we don't care which country this is, we're just trying to get the raw data and compare them. You're just saying we could just take %180 of values, and that will just give us and that will just give us the values.
right? Because we
Yeah.
know the data are every day, and they all begin on the same date.
Right. So then we just want to say hash greater than 0, right? And then
hash greater than 100 probably.
well, but that's going to give us.
Okay, this will be since it's 0, but again, the usual metric I've seen being used is they do greater than 100 because there's too much weirdness that can go on when you have just a couple of cases. Like the speed of spread is too variable.
Okay, all right, fine. So so what we want to do here is that mapped over okay, so this is going to hopefully give us all of the different places. And so now for each of these,
you could just stick this into list plot to see what it looks like. Yeah, list line plot.
Oops, what do I want to do here? I want to say %184.
Wait, do you need to
concatenate
it in some way?
No, the problem is there's lots of different length.
No, I don't think that's the issue. I think you just need to concatenate or something. I don't understand why it's step 3.
That is clearly not what we want.
That's not what we want.
Well, let's just look.
When we did it on just the one-time series, we just had a single list of values. And
this isn't. Why is this step? This is not step 3. This is. Maybe we need to. You know what the problem is? The list line plot is not realizing that it should start plotting everything at 1. I suspect.
Well, we could do list plot with join true.
Yeah, just I think it should work. Just try once more. Try list plot. I'm not sure if you did something
delete
strange.
cases.
I'm not sure. Well,
there you go.
What the heck is all this?
Those are countries or places where there was not a lot of disease and it leveled off quickly. And the others
but there are some of those, it goes up to like thousands of cases.
Yeah, I mean, those might be for, like the state of Rhode Island that doesn't have anywhere near as many people as California.
So those could just be, well, no, but there's nowhere where they've leveled off because they've hit the ceiling.
Well, let's label these. Let's label them. I mean, so let's see. How do we want to do that? We want to do that by saying
you don't want to use %175.
Right.
We'd have to get the administrative division or the country.
Yeah, right. So instead of confirmed cases here, we want another thing as well. What do we want here?
You want the list of the administrative division, comma, the country, or whatever order you want, comma, the confirmed cases, or like mapping to the confirmed cases. You should arguably do it as a pure function.
This?
So not quite. Just make it put an ampersand after it.
After this?
Yes, and then write hash administrative division, comma, hash country, arrow.
Oh, yeah,
hash
no strings. Cases. Yeah.
And you're proposing that I do this?
Yeah.
Okay.
So try that.
Okay.
And it's fine that some of them say missing, not available. I mean.
Okay. Yeah. All right. Okay. So now what am I doing here? So then what I want to do is I want to do the same thing that we did here of select on the time series. I want to map that select.
There's some super clever data set ways you could do this, but
yeah. Well, I can do
it. Also, don't remember this is a list of rules. This isn't an association. the data set.
I understand. So what are you saying? So why don't I make this normal, and then
say association of normal of that? Yeah.
Why do I want an association? Oh, I see. You're saying make that an association.
Yeah.
Come on, wake up.
It's just a displaying. If you put a semicolon after it, would probably be instant.
Right. Okay. Fair enough. Okay, so there they all are. Okay, now what are you saying? So now here, what we want to do is we want to map over that, just this thing here, right? That's all we need to do.
Yeah.
We want to map it onto the value of each one. Yeah, that's right. If it's an association, that'll do it to the value. That's right.
Right. So, okay. So then,
by the way, how the time series for the Diamond Princess cruise ship is the only one that's not where it goes down the number of confirmed cases.
Why? Because they left the boat, or what?
I think that's what's going on. If you look at the time series.
Oh dear. Okay. So, let's look here at let's see, what did I call this? I called this
data.
That was a really brilliant name. Okay, fine. So let's call this selected data. Is that over data? Okay, so now let's just check that we have something reasonable here. Okay, fine. All right, so now,
but we've lost the labels.
No, we haven't.
No. It's just because he said part. It should still be there.
Okay, right.
I think it needed this delete cases thing here.
Let's find out. I think it actually doesn't. I think that the reason it was having a problem is because it didn't know whether or not to interpret the list of lists as a list of two-dimensional coordinates or a list of different things to plot. But because it's an association, it's not ambiguous anymore.
Well, but it doesn't like it.
Well, okay, maybe you're right.
Lest we should complain about this to the
okay.
Wow.
Wait, do key value map and make them tooltips or call outs.
Yeah.
Okay. So what are you suggesting? Key
value map of, say, call out of #2, #1. Although tooltips might be the thing to do. I'm not sure.
I think tooltips are the story.
Yeah.
Okay, so let's find out what this is. Okay, that is Guangdong, China.
Maybe these are all just regions of China.
That's
yeah.
Amazing. If that's true.
Those are provinces.
Yeah.
Yeah.
All China.
Yeah, so those would be the administrative divisions, and the ones on the left that are going up through the roof would be the countries.
Well, let's pick. Do we have ones where let's pick things which are only countries? So let's do a key select on.
Key select that the first thing is missing.
Yeah.
Right. Key select on.
Missing Q. You could do you can use function composition.
Okay, tell me what
to
do here.
Missing Q at star first.
Okay.
The first argument should be S data.
Right. Okay, now let's say list line plot.
Well, you need the key value map as well.
I know.
Maybe you should just.
So Christopher, you're a fan of @* instead of /*?
Well, for data set, I use /*, but for everything else, it's @*.
Okay.
I think /* is a bit too bizarre otherwise.
Okay, let's take a look at this. All right, so that is the cruise ship. That is Japan. That's Singapore. Okay, so let's do this on a log plot.
So those are the ones with the low, basically the ones with the low R. Oh, you can say list log plot. I believe list log plot is.
Yeah, I'm going to do that
by default. Okay.
Oh, that's much better.
Oh, it's nice that most of them are a bit less than linear.
Yes, it is interesting. Okay, so that's the cruise ship. That's Japan. That's Singapore. That's South Korea. Where's China? Italy, Iran.
I think China. I think it doesn't.
Oh, it wasn't. It was never supported.
It only has the provinces.
I see. There was no aggregated data there.
There should be. I know in the original Hopkins data that it's called mainland China for the country.
I see, but I didn't realize that there was that even in the who knows whether these things are complete. What the heck is that?
I mean, you would hope that they are sublinear, because if they were, the basic model suggests that unrestricted complete flow, it's exponential, in which case it would be linear here. But so you'd hope that with mitigation methods and stuff like that, it wouldn't be doing worse than just unrestricted complete spreading.
Mm-hmm.
But I mean, it's also interesting to the extent to which these things, I mean, I don't know to what extent it's really true, but the extent to which these all seem to follow the same pattern. I mean, because on this log plot, the difference in populations is only going to show up in a shift.
Right.
So it's like the only places that are really okay. So this is South Korea, and that has that has a definitively different shape. So is there some way we can characterize?
Same with Japan.
What's that?
Same with Japan. The green one that's down below, I think. The one that's basically linear.
But with a lower...
it's linear with a lower, yeah.
Yeah, that's weird. Right, so I mean, all of these seem to have about the same exponent.
Mm-hmm.
Except for Iran that had an initially higher exponent.
Slightly.
And what are these? Singapore, lower exponent. Hong Kong. I am now really curious. Let me look at something.
Singapore, Hong Kong, and South Korea had very extensive testing and quarantine measures instituted very quickly.
Right.
Yeah. I don't think Japan is particularly warm, if that's what you're trying to look at.
Yeah.
Well, yes, I was trying to look at that.
That aspect of these data I'm not that familiar with, but those three countries that I named do stand out that way. But as far as what's happened in the others, I don't have the details.
I'm just curious whether, so Japan has not been warm in this.
Well, I don't know. I know Japan often is not very warm in the winter.
Why didn't I get time series here? What did I do wrong?
I'm not sure. I think you have to specify the granularity in some way.
Okay, hold on. Date. Oh, just a second. Maybe I have to say time series. Okay. What did I do wrong here? I'm very confused by this.
I think again you have to specify the granularity in some way. You should just go to the documentation for air temperature data.
Yeah, I was doing that. I wasn't seeing what air temperature data, location spec, date spec.
Just go to the example. Yeah, the step specification for step. It was just saying it.
All right. Okay. So 1 day, let's say.
I think you can just say quotes day.
I bet this will work. Up, you are right. It doesn't work. Oh, come on. What am I doing wrong here? Maybe the country doesn't like the fact that I'm asking for a country. Maybe that's an aggregator.
That's
Yes, that's the problem, I think.
Yeah.
That's the problem. I think because it wanted me to average. It was averaging there. Okay, so let's look at that. So let's say dateless plot of that.
I mean, I think you want to say the mean of that. You want the mean temperature over that period for the different places, and you want to plot that against the slopes of the logs of these things.
I know. So let's do this for. So what we need is for each country here, we should take. Let's just take the capital city just for simplicity.
Yeah.
Right.
Okay.
So I mean, it's not the best thing to do, but it's something to do. Okay.
I mean,
so
the only problem is, okay, go for it, but your plot's not going to be super interesting because basically the base of the exponents is going to be the same for almost all of them except for these three. And so they're only going to be basically 3 data points that are actually interesting.
Well, wait a minute. What was the answer for Tokyo? 50 degrees Fahrenheit, basically. Okay. And Seoul, probably not warm either.
Seoul also gets very cold in the winter.
40 degrees. Okay. So much for that. Okay. Higher humidity and lower infection rate. That's interesting. I wonder if we have the humidity data. I think we do. Let's take a look. I bet these are not humid, but let's take a look. Weather data. Humidity. Okay, so I want weather data, location, property, date. Okay. So let's just do this. Let's say location, property, humidity. That varies a lot. It's probably raining some of those days. So let's just see what it looks like for, I mean, it did go quite high there. Singapore as a city. Well, it's actually interesting. It's not so convincingly higher in Singapore. Okay, let's look at Seoul. Let's compare that to some place. What about Milan? No, there's no effect here. I mean, there's nothing. If we look here at, let's see, if we look at the histogram here, well, we could just, yeah, we can look at the histogram. That, compare it to Singapore. Okay, all right.
They're on different scales. They're on different scales.
Yeah, they're on different scales. Okay, so if I look for the mean for this one, let's actually do. I wonder, does this work for this? No. If I did that for
say mean round of values, yeah, that should work.
Okay, 0.7 for Milan, and 0.76 for Singapore. So I don't think there's a huge effect there.
Yeah.
Not really a convincing. I mean, just to compare here, let's do the same thing for temperature. (7.5 degrees centigrade there. And
it's a funny coincidence.
What?
It's funny that it's 7.55 and the other one is 0.755, but one of them is temperature, one of them is humidity.
Okay, and this one was 29 degrees centigrade. So that's a substantial difference. And if we did the same thing for, I mean, we already know the answer, that it's for Sol 3.6 degrees centigrade. So that's not the story. And let's see, someone is suggesting beautiful query for aggregating per country. Very nice. Well, anyway, I'm not sure that there's more we can figure out right now, but unless people have questions or suggestions, we probably should wrap it up. This was interesting. I mean, I'm afraid that my main conclusion is it's pretty hard to know what's going on. You know, it's not one of these cases where you know, where the modeling is obvious.
No, and I think if you had a hypothesis about something, a specific hypothesis, it would be hard to perhaps do an appropriate test of that to see if it.
Let me make a comment about this, okay, which is a little weird. I mean, the fact that these are so close, I find interesting, because to give you an example of something, okay, so when we were looking at this Facebook data, now I admit that the online world isn't the same as every other world, but this was a plot of the median number of friends by location, okay.
I think this is just a purely online effect, but.
Well, so your claim is, I mean, that the net, you know, with respect to those graphs, that either, I mean, there's several possible hypotheses here. Either the typical number of social contacts is just a constant of the species, so to speak, and it's the same in every country, and that's why these you know, curves have the same slope. Or for some reason, what matters is some, I mean, where else do you determine? What determines that slope? Or is it determined by something that is some, you know, extreme case in the network that's very insensitive to the averages? Either the averages are the same, and that's what it's sensitive to, or it's not sensitive to the averages, it's sensitive to something else. And what you're seeing here is an intrinsic property of the disease, not a property of the social network somehow. You know, and again, there may be all kinds of, it still really kind of bugs me that these are all so parallel.
It would be interesting if we could have similar data for another disease. I mean, the only one that I can think of that there might be something for would be influenza.
Yes. Well, or a particular strain like H1N1 or something.
Yeah, that was in a number of different locations.
Right.
I mean, I guess it's basically just telling you that there's, you know, that the structure of the social network is relatively similar, or the contact network, I guess.
Yeah.
Japan. I mean, just, I don't understand these ones here. Well, I mean, that one, okay, but Japan is clearly different. In this, you know, that slope is clearly different. And the cruise ship, who knows? Yeah, it is really strange that these are so similar, except for Japan. What is it? What actually happened there? Is that a I mean, I would have expected that one would be full of people, you know, going on the subway in Tokyo and things, and being exposed to just gazillions of people.
Well, Japanese culture does stay far away from, like, people in Japan do stay far away from other people within Japan. They're, like, culturally speaking, they're not very touchy-feely, and they do wear masks as a general.
You mean just as a matter of being out in Tokyo because of the air quality and things?
Yeah, and even like familial relationships are very different, very.
Okay, well, with that anthropological claim, what would you claim about some of these other countries?
Physical contact.
No, but what Stephen was saying about the subway, the Tokyo subway is extremely crowded.
Right, but everyone kind of keeps their faces like and their hands to themselves. It's like you're wrapped up in a.
But at least the last time I was there, which was a very, very long time ago, sometime in the 80s, I think was the last time I was trying to navigate my way through the subway, not knowing any Japanese. Yeah,
I was there 20 years ago, and the signs are Japanese and English, so I didn't get lost. But I mean, they're everyone's hanging onto poles or the straps. So there's a lot of that.
Well, anyway, so I mean, there's an effect here. I mean, there's something different, right? There's something definitively different, and I don't know. Okay, there's Iceland. What does Iceland seems to have a lower slope as well?
But that's
tiny population.
Kind of hard to tell.
Yeah.
I mean, the other thing, by the way, is that a reason why it's surprising that they're so close together is that all these countries have different testing strategies, in terms of whether they're testing lots of people or just people who seem sick, or whether they're testing, etc.
Well,
so it's honestly kind of surprising they're so close.
Yeah, right. Exponentials are fairly unforgiving. I mean, also, so long as they didn't change their testing strategy, you're still going to get an exponential.
Well, you're right. But I mean, as long as, like, you could imagine, for example, that some place maybe has a limited number of tests and that they're testing a fixed number of people, right?
At least initially. Yeah.
And so it's kind of like if the stuff like that was happening, then you'd expect to see weird curves, but in fact, it's not really.
Well, it's interesting, and there's probably something to learn from this. And now, in this, at least in the very inadequate data we have here, Brazil seems to maybe have a lower slope, but you're not going to convince me that Brazilian culture is a okay. UK might be an avoid people culture. Who's to know?
That's true.
I don't know if that's really
well, but if you look at their slope later, they're the same. But
yes. Well, okay. Right. I mean, did Japan implement some social distancing strategy early on? One of the things that I don't think anybody has been collecting, and it would really be good if they had, obviously one can go back and do it, is just go curate all of the, social distancing measures that were taken. Like, I mean, I have seen some data set of when schools were closed in different US states and things like that, but it'd be nice to know. I mean, one was looking at this, presumably these curves will have an effect as a result of various measures that were taken, and it would be nice to be able to see what I mean, this is not good. This feels very inexorable. That even though these countries are all different and have lots of different characteristics, the slope looks the same. Well, except for Japan, most interesting. All right, well, we should wrap up here, but interesting stuff. Thank you all for joining us, and maybe we'll if we can figure out more ways to analyze this data or more robust ways to come up with conclusions, maybe we'll try and do this again. Thanks all. See you all later.